quite enough. So we're very pleased to have for our colloquium today Eric Bedford from Indiana, who is visiting us at the Institute for Topological Sciences, and who will talk about automorphisms and pseudo-automorphisms of complex manifolds.
Okay, thank you very much, Well, it's really a pleasure to be here, and I'm glad to be able to tell you what I work on, and I hope you might find some of this interesting, and those of you that I haven't been talking with before, maybe we can have something to talk about. So I'd like to start with some things that are well known here. So I'm interested, suppose we're looking at a mapping F from C2 to C2 that's a polynomial automorphism. So that means it's a polynomial mapping that's invertible, and the inverse then is a polynomial mapping. And you're interested in studying the iterates. And there are, in fact, lots and lots and lots of polynomial automorphisms. So how do you know what you want to choose to start working on? Well, one thing is, if you're iterating mappings, if you take a conjugation with something or other, the iterations of this mapping and the iterations of that mapping will be conjugate to each other. So you're really interested in conjugacy classes. That's one piece of data. What else are you interested in? You could ask, well, what's the degree of F? Well, F is a mapping, F is P and Q, say. So these are functions of two variables, X and Y. The degree of F, just naively, is the maximum of the degree of P, first coordinate, and the degree of the second coordinate. And so you would really want to, if you're going to study the iteration of something, you want to study something with degree bigger than 1. And so that would make sense. But a problem with the degree is if you're looking at the iteration of F, and you take the nth iteration of F here, the degree of that thing will be less than or equal to the degree of F to the n, greater than or equal to 1. But besides that, you can't say much of anything, so the degree by itself really is definitely not a conjugacy invariant. So just because you have some polynomial that has a very large degree doesn't mean that you're not, for instance, conjugate to a linear map. Okay, you just can't really tell, because if you take some very large you take some automorphism of a very large degree, conjugate a linear map, you could get something very large degree. And so a good concept to consider here is the dynamical degree. Okay, I'll call it delta of F, which will be the limit as n goes to infinity of the degree of F to the n and through. Okay. And the dynamical degree is a conjugacy invariant. And you can see that it's much harder for this one to be strictly positive. And so these are the ones you might want to look at. And this is exactly what's addressed in a theorem of Friedman and Milner. Okay. And what do they say? Well, so I'm supposing I'm having a polynomial automorphism. They could say, at least I'm maybe rephrasing the results. Suppose you have a mapping whose dynamical degree actually is bigger than 1. Then, so this is an if. Then F is conjugate. So let's see. I'm going to say several statements. This isn't really presented in a perfect way here. Conjugate to a composition of Henon mappings. These are Henon mappings. The generalized Henon mappings, which have, very specific form.
C2.
Pardon me?
C2.
C2, yes, exactly. Right. So we're right now in C2. C3 is a story where the structure of the polynomial automorphisms is very far from understood. But okay, the point about this is some very specific form you can look at your mapping in, and in fact, in this format, when you go to iterate it, the degree of Pj, well, and then I should say the dynamical degree of Hj is the same as the degree of Pj. And so, excuse me, what's the first coordinate? Y. Should have been
what's after Pj of y?
Minus, okay, so this is some number, delta, of Uj of x. So this is some,
No yj on the delta?
excuse me? What did you say?
There's a sub j on the delta, or is it just a number?
Yeah, this could be, this number could change.
Oh, I see.
With all these, you might have a different number. And so in particular, a thing that's taken me many, many years to appreciate, in particular, the dynamical degree of your mapping is an integer. Namely, if I go to this is the degree of Hj. When I go to compose them, I just multiply these degrees. The product of the degrees of Pj's, you get this thing as being an integer. And I believe they explicitly pointed this out. And of course, in my youth, I just said, never. But then over the years, I've been appreciating that fact more and more, that it is an integer. So what I want to discuss now is to look at a more general situation. Suppose we're trying to look at the situation where x is compact. Okay, we're looking at some kind of compact complex manifold. In fact, for everything I'm talking about, it might as well be projective. A lot of the things I'm doing are my own self-taught ways of trying to use a little bit of algebraic geometry. And since there's a wealth of algebraic geometries here, if somebody takes pity on me and wants to help me out, that's very welcome.
Just to make sure I understand the story in the just in C2. So
yes.
There's another invariant that would be tempting to look at, which would instead be there's a topological degree. It's a
Exactly.
Such a map. But the point is the degree of the polynomials can be much higher, because you can just take something like the identity in one variable and then add on something very high degree in the other variable. That's an invertible map, right? So if you take
That's an invertible map.
yeah.
And when you go to take the dynamical degree, that other thing just disappears.
So does this, in fact, this converges to the topological degree? Is it?
Oh, no. Topological degree here, we're looking at invertible mappings so that they're all one-to-one.
Oh,
so
I
the
see.
topological degree is always 1.
I see.
So these guys here are invertible. These are diffeomorphisms of C2.
Right.
But when you go to represent them, this mapping has degree. Okay? So it's a little bit different than in the case of one dimension. In one dimension, what you call degree is the topological degree as well as the algebraic degree. So here we have.
In fact, that's the example you said. He said add a term in the other variable. One of the variables, but you flip them there. But
Right, and it's exactly on purpose that we flip them, or they flip them. This is the one where when you compose these guys, the degree grows exponentially.
because of the flip.
Yeah.
Sorry, I also have so in this theorem, is this for any arbitrary f, or are you somehow assuming that
I'm
this
sorry,
limit
these are
exists?
polynomial.
Yeah, polynomial, but
Yeah.
so is the conclusion also that this limit always exists, or?
Yeah, the limit here is, this limit is always going to exist because this kind of inequality means you have something logarithmically convex. So you always have a limit. Okay, so I want to look at a rational map. So what is a rational map? A rational map is something that, since I've got the flaky dotted arrow here, It's not actually a genuine map, but it's something like this. I have a manifold up here that serves the purpose of being a graph, and I have a couple of projections onto the first coordinate and onto the second coordinate. And the assumption here is that pi1 is onto, and generically, pi1 inverse exists almost everywhere. It's a mapping that is generically one-to-one onto X. And so my mapping then, F, is defined by taking pi1 inverse and following it by pi2. So this is a way to find something. This is my mapping here. And I claim that there's a well-defined mapping on cohomology. And the point is here, if I start out with a smooth form, I have a smooth form and I have a holomorphic mapping, it's not a problem. It's well defined to pull back to the smooth form up here.
Any type form in particular?
Well, whatever my type of cohomology is. Okay. So if it's PQ cohomology, it's PQ. And then I can take this guy, I'll call it R. So this is a smooth form, and this means I'm just going to reinterpret this guy as a current. In other words, it's like if you have a smooth function, you can reinterpret it as a distribution. I can just reinterpret this guy as the dual space of the test forms. If I have a current, I can push it forward. So F star of the class of alpha is going to be, well, I'm going to take alpha and pull it back, and I'll reinterpret it as a current, and then I'll take this pi1 and push it forward. Okay? And I'll look at the class that defines. Okay?
So pi1 is a proper map.
Yes. Yes.
So you're actually, gamma is actually compact.
Yeah. Gamma's compact, yes. Yes. Yeah, sorry. Okay. So this is F star. Now, as you can say, people say there's no free lunch. This was handed to us awfully quickly. There are problems, and that is that F star is not necessarily factorial. Or maybe the passage in the sense that F squared star may or may not be equal to F star squared. And also, if you think about the intersection form here, that may or may not be preserved by F star. So you got something for sort of free, but it may not, it may be worth what you paid for it. So what's an example of this? Let me consider J.
So F star is not a homomorphism of rings. It doesn't have products.
It doesn't necessarily preserve the product structure. You can see that there is smooth sailing on the first step. Okay, but if you're multiplying two things and then you're considering them as currents, you've already expecting to be in trouble. Okay. So
you said gamma can always be compact. How do you?
I want gamma to be compact. I mean, I'm just
Part of the definition.
Yeah, definition. Yeah, gamma to be compact. It's a graph. I mean, I'm going from X to X. It's the graph.
It's a subset of X times X. Maybe you want to take a resolution of that.
I could start out with the graph, just the literal graph, and then resolve it. Okay. And then.
Manifold context.
Right. Right.
Well, you started with C2.
Excuse me?
You started with C2, so
Over here I started with C2. And here if I take, so I started with F in automorphism of C2. If I go inside of P2, F will extend to a meromorphic map of P2. And what happens on P2 or C2, I'm going to add on the line at infinity, okay? And there'll be some point, the ends of one of the axes axes, I forget which one is which, will blow up to the whole line, and the line will go down to the end of the other axis. So what happens when you extend this thing to infinity in P2, you've got something that you've got a point of indeterminacy. That point blows up to the whole line at infinity. The rest of the line at infinity is just mapped, completely collapsed at this point. Okay? And otherwise, it's the same. In C2, it's the same map as always.
So in this case, gamma would be C2 blown up at a point?
Oh.
Or P2, I mean?
So in this case, gamma would be the graph, let me see, x, I screwed up with my notation, x, y, x, y. So
That's right. But we could have to plot P2.
I can take f of xy is xy. Okay, I can take this inside of C2 and then change its closure.
And then if you resolve that, it's always a blow up P2, because it's something birational P2, and then the projection.
Well, if I blow the, So anyway, if I blow this up, I mean, this.
Oh, but wait, he asked, what is a closure? He didn't ask about blowing it up.
Oh, I forget what. I mean, it would take me. I've got. Sorry, I can't figure it out. It would take me 10
But
minutes.
no, but it's always tries, always blows it up until you get something that's smooth. So gamma a priori might not be smooth.
This may be this out at infinity. This may be singular, but I'd have to think about points at infinity. Sorry, I can't answer
Right,
you.
so you have that option, why not take it? So it's always a subdivided x times x, and you can always find it.
Right, you could always
blow out and make it smooth.
So let me give an example here. So J, this is the standard Cremonian evolution. The Cremonian evolution would take homogeneous coordinates just to their reciprocals. That, okay? So J is mapping things like this. So J, so this is the same as x1, x2, x0, x2, x0, x1. Okay, so this is a quadratic mapping. And if I look at cohomology, if I look at H2 of, so I take H2 of P2, that'll be with coefficients in Z. That'll be Z. And if I look at what J star is doing, this is just going to be multiplication by 2, because I've got a quadratic mapping. And if I take J squared, I get the identity. And the identity, of course, is just multiplication by 1. And so you can see that this mapping, this fails for this mapping. But what's happening here is this involution has very famous structure, E1, E2, and E3. If I look at these intersection points, or actually I'm going to call it E0, E1, E2. So this line then would be the line x0 to 0. And under this involution, E0 goes in back and forth, x0 equals 0. So I've got this behavior going on. And so I can create a new space. Let's see if chalk wants to work. I can blow up E0 and E1 and E2. And I get a new space that, if you don't know exactly how to blow things up, let me just say that you have a new thing. You've constructed a new space over here. This is a manifold. And the projection is singular along the, it's a smooth mapping, but it just happens to collapse these three curves, E1, E2, and E0, to points. Okay? And when you go to compute, okay, H2 of your new space, is now generated by the class of a general line, E0, E1, and E2. In other words, when you do this, E0 has the interesting property that it's a subvariety of X, closed complex submanifold that maps down to a point, but if you go to try to wiggle it, you can't wiggle it. It's a rigidly embedded thing, so if you try to perturb it a little bit, you will intersect E0 again. So this white curve is a smooth curve. These two will intersect, but if you compute the intersection, the orientation will be backwards, so it's a negative thing. So if you take E0 and intersect it with itself, you get -1. And for the people that do complex analysis or whatever, you know that down here in little neighborhood of E0, that's a little ball inside of complex 2 space. You know there are no closed submanifolds, complex submanifolds inside some bounded domain of complex C2. And that tells you, if you had a small perturbation, this would perturb, it would project at something down here. That perturbation can't be complex. Okay, so E0 is a rigid thing, and it actually is generates a new non-trivial generator cohomology group. And so if you
Good proof.
at least I got the sign right. So if I look at this thing, in fact, it's a little exercise. It'll take a few minutes, so I won't do it. But I get a 4x4 integer matrix, and I get this matrix and the matrix squared. In fact, will be better. So when you in this particular case, you have an involution, and the involution fails this property. Okay? Fails that property because J star itself, just on projective space, is 2. But when you extend it to the manifold X, that 2 will become a 2 up here in the upper left-hand entry of the matrix, corresponding to what happens to a general line. But then you're going to have other things throughout the whole matrix, and this will actually be a matrix that when you square it, you're going to get the identity.
Oh, you didn't prove that.
I didn't prove that. I'm just
asserting it.
I asserted it. Right.
You indicated the proof?
Pardon?
Did you indicate the proof?
I could indicate a proof.
No, I just wanted to.
No, I did not indicate a proof. No.
Okay.
I just said, if you want, I could. But here's what I wanted to get to. So my point here was that when you have a rational map, you can easily pull, or even it's easy to define the pullback on cohomology. And there are a lot of cases when you want to define the pullback of cohomology, it becomes much better behaved when you modify your space by making blow-ups. So in this case, I modified the space by blowing up these 3 points of indeterminacy.
I didn't quite understand what that square matrix was.
The matrix. Well, if I go to write it out like this, it'll be -1, -1, 0.
No, I mean, what is this geometric interpretation?
Yeah.
Okay.
What is it conceptually? What is it?
What is it conceptually?
I mean, isn't the geometric picture that you really, when you're pulling back and pushing down, but you're taking really the Poincare dual of the generator, pulling that back, and now interpreting that as a homology class, pushing that forward.
Yes.
And then, so what happens is that under this Komodo transformation, the points get interchanged with the lines, and so a line goes over to something which is actually 3 adjacent sides of that hexagon, and then you flow down the sides, you get 2 lines going to a point.
Okay, you have been explaining this piece, maybe. Okay, let me explain.
It's only one generator.
Let me explain. Well, that's one of the generators. Let me start off.
Oh, it was downstairs on P2. the key thing is on P2, there's only one generator, so you just have to trace it through.
Right, right. Let me just first mention E0. E0 maps to this one, sigma 0. Now, what's the generator here? L is
Yeah,
the...
but why don't you answer Jack's question? What is that matrix conceptually?
I'm going to tell you. Well,
Conceptually.
well, we all have different ways of conceiving things. Let me make a try here.
The matrix is what it does on the second homology of P2 blown up at 3 points, which has a rank 4 second homology group. And so you're writing down the matrix of that transformation. But the thing is that when you blow down, you are only actually you're looking at something. P2 only has one generator in the second homology.
Okay.
So you only end up seeing that little corner.
Right.
Upper
If I
corner.
may, I think the question, did I understand the question correctly, that you were asking what is this matrix of, not what the numbers are?
Yeah.
So maybe you want to say that what data are you encoding? You're encoding some intersection numbers or something with something.
Let me see. The data here is this is the image of L, represented in terms of homology, cohomology. This is the image of E0 in cohomology. So the columns are the images of the various generators.
And the homology of what?
P2 blown up at 3 points.
The P2 blown up at 3 points. I'm over here, down here in the space X, or up here in the space X. And so I'm looking at, say, E0, for instance, E0 is going to E0, that manifold maps to sigma 0, that manifold. Now, what's the nature of sigma 0? Well, if I think of a general line, this would be a general line, but when I slide it up here, a general line would also pick up E1 and E2. So it's a general line missing E1 and missing E2. So that's for me, that's the meaning of this column here. E0 goes to a general line missing E1 and missing E2. Okay? If I look at a general line is going to go through, it's going to cross all these sides of the triangle. If I pull it back, that means the pre-image has to be crossing all of these, the sides of the triangle go to these 3 blow-up fibers. So I'm going to have some curve that's going to have to go through all 3 of these guys. Okay? But I know it's going to be a quadric, since I have a degree 2 thing. So I'm looking at a conic here. I've got a conic that's crossing all 3 of these things, but not containing them. So that means degree 2 is I have a conic and I'm missing all of them. I'm not actually, when I pull back, I'm not actually containing these blow-up fibers here.
So this matrix represents an involution of gamma?
In involution of cohomology,
You said a gamma.
yeah, I was thinking about this. So in fact, in this particular case, the graph gamma looks very much just like the mapping itself. And so this mapping is also an involution of gamma, since our mapping is just an involution.
It might help to, on a hexagon, if you color the sides in 2 colors, where you, say, take the big yellow chalk and make half of them bright yellow, and then the other some other color. So on one side, what you're doing is you're collapsing, so you color 3 sides.
Here?
Yep.
Okay.
And then the 2 that,
You want all 3?
yep, all 3.
Okay.
All right, so on one side the map is that, so that's 2 blown up at 3 points. On one side of the map is collapse the green edges, and on the other side it's collapse the red edges.
Right.
And so the point is the Poincare dual of a line. I mean, the inverse image of a line becomes, let's say, the bottom edge and the 2 adjacent ones, right? And now if you push that down, you get 2 lines through a point. So the induced map actually it sends the class of a line to class of 2 lines.
Okay. So that's
That's the key.
okay. Now I've been, so let me talk about one other thing. Here was this here is our panel for degree. And so in general, suppose you have, what I want to do is define, let me just copy so I don't get inefficient. So I want to define other dynamical degrees. This will be the limit is n goes to infinity. I can take f and iterate it n times. Okay. Pull back cohomology, look at what it's doing specifically on PP cohomology. Okay. This is a finite dimensional vector space. I can take the norm, in terms of any particular norm, I don't care what, take the nth root, and then that will be the dynamical degree acting on PP cohomology. And so what we were talking about before is this thing here. Let me just say this so much. And so here's a comment. Suppose F is regular, or holomorphic, or whatever you like to use. Then what is this? Then delta P F is the spectral radius of what happens when I'm looking at this mapping this cohomology to itself. In other words, when you're doing this kind of thing, this is just taking the spectral radius of a linear transformation. And so it's the largest modulus of the largest eigenvalue. And so easy theorem is that if one of the delta p's is bigger than 1, so if I have some, so in other words, if I have a mapping, and let me say, let F be an automorphism. Suppose I have an automorphism. Oh yeah, one thing I wanted to say here. Sorry, I forgot a comment I wanted to make. So one thing that's always true is that delta 0 is 1. Okay, just for no, that's for. And delta of the dimension, that delta is the topological degree. Topological degree. In other words, if you're. So in case we're talking about automorphisms, this would be 1. So you have a number of dynamical degrees, okay, from 0 up to the degree of this dimension of the space. The endpoints are both 1, and then in between, I'm going to have something that in fact is concave, log concave. So an easy theorem here is if one of these guys is bigger than 1, then all of the dynamical degrees are irrational, okay, for j between 1 and the dimension 1 minus 1, and they're the spectral radius, but they're algebraic. Okay. So they're irrational, but they're algebraic. So this gives you a way of seeing that these mappings actually would never be extendable as automorphisms to some compact manifold. Did I say that? I forgot to say make my hypothesis X compact. Okay. So these wouldn't ever actually extend to automorphisms of compact manifolds because when you have an automorphism of a compact manifold, dynamical degrees are never rational.
How do you prove that? How do you prove that?
Oh, let me just say it's a really easy exercise using, so here we have this delta is a root of some x to the n plus a n minus 1, x to the n minus 1, plus 1. Okay. So it's a thing here about you've got an equation like this, the roots that are not
rational roots are constrained.
Yeah, the rational roots are constrained, yes. Yeah, so it's...
So the coefficients come from where? Can you read them off from the original polynomial? Something about the original polynomial?
So this, oh yeah, so the thing is, I can represent this by integer matrices. So in other words, I can work without loss of generality. I can assume that this is an integer matrix. So this is the spectral radius then is gotten by looking at the characteristic polynomial of an integer matrix. So I'm going to have a matrix looking like this. The fact that it's an automorphism, this has to be 1. Okay? And I always have a monopolynomial, and I'm not thinking quite quickly enough, but you can see immediately that there can't be any rational roots to this thing.
You're saying it's always an algebraic unit?
Always an algebraic unit. Yeah.
Well, you could bring everything except the constant to the other side, and then it would be invertible. So if it was rational, it would be an integer. It was invertible, so plus or minus 1.
Okay. Yeah, good. So our hypothesis is that this guy is bigger than 1. So, thanks. Somebody would save me. Okay. So let me describe the general plan in dimension 2. What's the story in dimension 2? Or let me just state a theorem here. There's a theorem in Jan and Min and Bob and Voltron that says, suppose we're looking at a rational. So this, yeah, sorry. The other thing I wanted to say was that the significance of these dynamical degrees, the hard theorem, Gromov, Youngman, that is that if you have an automorphism, holomorphic automorphism, then the topological entropy of that is the maximum of these various. So these dynamical degrees give you the entropy of your mapping, the topological entropy.
Is this actually a holomorphic mapping?
I'm thinking if it's holomorphic mapping. Thinking here, if I have a holomorphic mapping of a compact manifold, then these logs of the dynamical degrees give me the topological entropy. And suppose I consider monomial mappings. Suppose I let A be an integer matrix.
Isn't this is Gromov's theorem for holomorphic mappings and Youngman's theorem for C-infinity mappings?
I thought there was an inequality or something, but maybe I'm wrong.
Gromov is upper equality and Youngkin is lower equality. Gromov is upper for holomorphic mappings and Youngkin is lower for smooth mappings.
And suppose A has eigenvalues lambda 1 through lambda k. So we're looking at a monomial map. Let's write it this way. Think of a monomial map F maps CK to CK, and I can take any compactification I want. They're all situated taking toric manifolds. And then the dynamical degree of FA. So of course, it's an integer matrix, but the integers don't have to be positive or anything. And I want it to be the determinant of A is not 0. And so the lambda 1. Okay, so let me suppose this is the largest. These are in decreasing order, then the product of the first P eigenvalues is the dynamical degree. So this is one case where it's actually been computed. In general, it's very hard to compute. In general, it's comparatively easy to compute delta 1 but all the other dynamical degrees are pretty hard to do. Okay. So,
can you say what the topological entropy is?
no. I mean, sorry, that would take me a little bit. Can I tell you later?
Or maybe can you tell why it's PP and not PQ?
Because when we're looking at growth, the let me see here.
So this is volume growth in all
We're-
dimensions.
We're looking at volume growth. Yeah, and so I want maybe in general, okay. In general, we're interested in the case where we have a Kähler manifold. And so let me tell you one other formula. So I'm sorry, I skipped a line in my notes here. The other formula I wanted to tell you was suppose omega is a Kähler form. Okay? Then the dynamical degree is gotten by you take the pth power of the Kähler form. Okay, so we're thinking, you know, with Gromov and Yamden, the idea is you're saying the entropy is very closely related to volume growth. And so we're looking at omega to the p, pulling it back. And then we want to see how big this is. This is a positive current, so to measure it, we can just take the dimension minus p. Take that integral and take the limit, and p goes to infinity. So this is the pth dynamical degree. This measures volume growth. In other words, we're pulling back this p codimensional volume form, and we're pulling it back, and we're measuring how much mass it has. And to do that, we just weight it with this. And so that's why we're just doing pp.
So you normalize things so that the volume of the manifold is 1, yes?
It doesn't make any difference. We're taking it through.
Oh, okay.
Okay. So let me say, what's the story in dimension 2? Okay. So there's a theorem on top. Suppose X is compact. Complex of dimension 2. In other words, it's complex surface. And we have an automorphism with dynamical degree bigger than 1. And then there are 3 cases. Either X is a torus, or X is a K3 surface, or a quotient of it, or rational. So I don't want to talk about these guys. I want to talk a little bit about the rational case. So what does rational mean? So there's a theorem of Nagata that says if you have an automorphism of infinite order, so this has to be infinite order, then you can in fact find a projection down to P2, and you can find some birational map down below, and you're mapping F up above is what you get by, the map F pushes down to some birational map G. Okay.
Are we in the context where F is actual automorphism or one of these things with bunch of indeterminacy?
This will be an actual automorphism. Okay. I won't, I can see I won't get to pseudo-automorphisms. But this is in dimension 2, everything that pseudo was in my title, but I guess this talk is less pseudo than I anticipated. So
What was the hypothesis in the Nagata's theorem?
Okay, Nagata's theorem is that if you have a rational surface, okay, so his hypothesis was x is rational, and there exists an f with f star of infinite order. So
rational means it can be obtained from P2 by blowing up and blowing down.
Right.
That's actually just blowing up.
So, right, this is just blowing up. Yeah. So you can just start down at P2 and then blow up. Okay. And the theorem of Kanta is sort of going through the Kodaira classification and checking what's possible and what's not possible. And these are the only three things that are possible. Here, if you blow down to, if you have something that you have to go blow up and blow down, if you end up at some other different Brook surface or something, those things don't have this property. So this is the picture. So in fact, it's possible to have a lot of, so I'm erasing my Cremona involution. There exist infinite families.
So in 2, it could be a quotient of K3, and so it could be Enriquez, and number 1 presumably also quotients of Tori.
I'm not sure about quotients of Tori. I didn't think about that. If you take quotients of Tori, you're going to do Kummer surface construction probably, and end up either K3 or rational. So if you take quotients of Tori and then resolve them so you get manifolds, you get one of these, I think.
Well, no, they're all the hyperelliptic surfaces. There are non-trivial elliptic curve levels.
Yeah, you have to have an automorphism with dynamical degrees bigger than 1. So I mean, those things sort of spread everything around, and so your quotient has to. Well, anyway. But the question is also, I mean, I'm not sure. I haven't thought about your question taking quotients of Tori. Anyway, there exist infinite families of case 3, and also there exist families in case 3 with arbitrarily large number of parameters. So, I mean, the tori and the K3 have some fixed number of parameters. It's the maximum number of parameters you can have. But there are families of, what I mean to say, automorphisms with rational surfaces with entropy bigger than 0 or delta bigger than 1, and you can make them have arbitrarily many parameters.
So, but the surface also changes in this family. Yeah.
The surface is always changed, yes.
So just clarification, is it possible to keep a surface fixed and still have one parameter family?
No. Well, let me see. But the variations are trivial. I mean, I don't know how to explain this, but you can't have serious changes in families. So these first families were all of the form L composed with J. So J was the involution we were discussing at great length. L means some linear map, linear automorphism. The automorphism group of P2 are the linear maps, and so you can start with the Cremona involution, follow it with certain special L's, okay? And with certain special L's, you can get, then you get an automorphism. Okay? So these have to be very carefully selected. And so I should just say here, the spaces that admit or that correspond to 3. In other words, the rational surfaces that correspond to this will be blow-ups of projective space, and all you have to know is where the points are, basically, but it's completely unknown. Let me see, what was I going to say here? So let me see. All. In other words, if you were asking what are all the x that can satisfy this condition 3x, that's completely, very much not known. Now what I want to do is I want to do two things, but I have to choose one of them. So the one thing is why, what is the purpose of doing all of this? So let me discuss that. The why. Okay, so what are we talking about here? We're looking for automorphisms such that when you look at what they're doing on cohomology, there's an eigenvalue bigger than 1. Okay? So let me just give I'm going to give 3 examples that I hope explains what is sort of the game plan for, I mean, this is sort of a 2-step project here. Step 1 is, well, what are the surfaces that carry mappings with dynamical degree greater than 1? And then if you have such a surface, what do you say about the dynamics? So let me first talk about just the simple real 2 torus. So I'm looking at F, that would be an element of GL2Z, just looking at the most pedestrian kind of torus here. I'm taking a integer matrix, invertible integer matrix, and so I'm going to have some eigenvector, some other eigenvector. Suppose this is an attracting eigenvector. That's a repelling eigenvector. I want to look at theta, one form, that defines this. In other words, I'm thinking of theta as being the one form that defines the stable foliation. Okay? Now, and suppose this eigenvector is 1 over lambda, that eigenvalue is lambda, this is 1 over lambda.
So you're not talking about conformal maps anymore?
I'm talking about a real 2-dimensional map, just a linear multiplying by 2 integer matrix. So if I take F and I pull back theta, I want this to be a vector that's expanded. Okay, so this is like looking at an expanded cohomology class. And so I can think of theta as being a measure on this foliation, the stable foliation. Okay? And so when I'm pulling back, I'm looking at the measure increasing. The measure is expanding. And what's happening inside?
What's happening here? That is actually an SL2Z?
Oh, SL2Z. Okay.
Well, so it's not a difference.
Okay.
But in terms of the fact that finding the automorphism of source on map,
so if I take a piece of a stable manifold, I'll call it L, then when I map it forward, it gets shorter. When I map it forward, it gets shorter. And when I map it backwards, it gets longer. So this is a picture here. If I wanted to look at the stable foliation, I can think of theta as measuring the leaves of the foliation, and I'm pulling it back, and the measure is increasing, and the leaves themselves, as I map forwardly, get smaller. If I didn't get my signs wrong or something. Now, there's another point of view on all this. That's the Ruel-Sullivan point of view. So he's supposed to have some mapping that's a diffeomorphism. You have some, so this is our axiom A non-wandering set here. And so we could have some directions that are expanded. Okay, so these guys are unstable manifolds. And these guys are stable. And so it's known that you have a measure nu of maximal entropy. And their approach involves finding geometric currents I don't know what I'm going to call these, but you have a current corresponding to the stable foliation, you have another current corresponding to the unstable foliation, and the measure then is the intersection product. So you can do that. Now the case of complex surfaces. Oh yeah, so the point here also was that when you're looking at the two torus, you can see in the two torus, everything is on top of each other. The mapping on cohomology and the dynamical mapping itself, you can see that there you have sort of the same picture, just reinterpreted. In complex surfaces, you have H2, the second cohomology, and you'll have some expanded direction, say. So this is an expanded direction in eigenvector and cohomology. You start, and then you'll have some other, so this one is the expanded vector. This is the other eigenspaces. So as long as I take anything that's not in the other eigenspaces, just a generic point inside of here, when I look at the pullback of this guy, and I normalize it, I'm just going to converge, let my starting point be d0. I'm going to converge to some actual unstable vector. Okay? Now, in the dynamical picture, so this is a picture inside of cohomology space. If I look inside of X, how can I interpret this? Well, basically, I can start with a generic, if I want to, I can start with a generic curve inside of X. And when I go to pull back, this curve I can think of as being the current of integration. But when I go to pull it back, that's the same as the current of integration over the pre-image. So I'm pulling this thing back, and I can take the limit. This is in something. And normalize it, and this will go to some current that I can call T plus. And so I just take this, and then I'm going to find some dynamical current T plus, and I'm going to do it the other direction. I can just start with something or else and go backwards by the inverse. Okay? And I can get a current in the other direction. And then it's a theorem that T plus, T minus are laminar. So here we have geometric currents, genuinely geometric. Here we have laminar, meaning that on sets of large measure, we have pieces inside there that are geometric currents, but they're not the whole thing. But we can also take the wedge product of these things and get the invariant measure maximal entropy. Okay. So
assuming the entropy is positive here.
The entropy here is log.
You're assuming something is big, right? There's an assumption here about the automorphism, right?
Oh yeah, I'm sorry. I meant to say that we're in this case where we're looking at an automorphism of dynamical degree bigger than 1. So that
limit exists.
Pardon me?
And this limit exists.
And the limit exists. So the claim is that these things exist. The limit exists, and for almost any starting place, you can take any sort of starting place, you could take any Kähler form, take almost any submanifold, and you pull it back. If you pull it back under F star, you converge to the T plus. If you can pull back to the other way, you'll converge to T minus. And so the idea of this is that once you have the dynamical degree bigger than 1, you will have, for a complex surface, you're going to have a unique attracting eigenvector, and you take anything and pull it back, and checking in cohomology, you have to go to that unique expanded vector. And so in particular also, it's a theorem then that if you look at it directly on the space of currents, these guys will go to the expanded current. And so this is
Any questions?
So in this theorem of Cantat, so all of these do in fact admit such maps, sort of indicated how to do the rational case for K3, for example.
Oh yeah. There are examples of all these things. The K3 surface, in many cases, you get your automorphisms by the Torelli theorem. So K3 surfaces in many cases can be seen as being defined as some lattice, and automorphism of a lattice with such and such properties. By Torelli gives you a mapping. So there are some specific mappings you can write down, but when they go to construct more exotic mappings, they're just working not so much directly in complex manifold space. They're working in
Just what the second homology is.
yes.
So are there any simple examples of maps of class 3 whose dynamics you really understand?
Oh yeah. Well, let me see. It depends on how thoroughly understand you mean, but there are. See, one thing I particularly like about case 3 is that you're working on a place where you can write down very specifically what your mapping actually is. And so the ones we understand the best are the ones that look like this. So A and B are parameters. Usually look like y minus A over x plus b. And so there is an equation. We have an infinite family of equations. If A and B are solutions to any of these equations, this thing will give us an automorphism. And so we understand certain things about these, although we don't understand that much more than we just understand about surfaces in general. So there's a theorem you certainly know about surfaces in general, that if you're looking at the number of saddle points, the distribution of the saddle points of period n converges to the measure mu, for instance. I mean, you know this about very specific, about all automorphisms in general, since you proved it yourself. So you know theorems like this about these, but we haven't really nailed down the topology. The topology is a question still.
how does a Julia set look like? Does it put this one on this line?
You're asking me questions that I'm asking myself. It's not clear, so I don't know. Asking what the Julia set looks like is a good question. I don't know what it is. We know several things about these mappings, but the basic questions, give me a picture of a Julia set for one of these mappings. Don't know.
For this theorem, is there something in dimension 3? Are there examples when you take a three-dimensional torus and you have an automorphism, when you have a Colloquium, or when you have a rational surface? I understand there may not be classification.
So, actually, for dimension 3, one thing that I think is an interesting thing, but it doesn't work exactly. Well, it sort of works. It doesn't work exactly the way I want it. In dimension 3, you can ask, does there exist a blow-up of P3 and an automorphism of positive entropy? And this is a question that doesn't have an answer. There is a theorem that says that if you just blow up points, then no. So you have to maybe blow up points and curves. You can find mappings, so this is the same harmonic involution, but in dimension 3. You can follow it with linear maps, and there exist these things which are pseudo-automorphisms. Spaces like this. There exist a lot of automorphisms or pseudo-automorphisms like that. Pseudo-automorphisms means that the only places where things go wrong are on in three-dimensional space. Only place where it's not a local diffeomorphism is on curves. So it means that you have a manifold, three-dimensional manifold, remove a curve, and you have another. The same guy, remove another curve, and your mapping is biregular between the complements of curves. But and so we've got mappings like this. But what you're asking, I think there is almost no knowledge about the three-dimensional case. Three-dimensional case is pretty mysterious.
But if you take just a non-trivial two-dimensional example and multiply it by P1 and just sort of take the...
Right. You could take a product. Right. But you want to have three-dimensional examples that somehow... so there are three-dimensional... Yeah, you want to make sure that they're not reducible in any way. And so another theorem is there exist maps like this with no invariant fibration or foliation. So fibration is less general. Foliation is more general. Since the foliations are allowed to have singularities, you mean there's no family of not necessarily closed manifolds that this family is somehow invariant. So there are such things, but